So there's a lot going on in the electron cloud of an atom. In order to make sense of it all, we need a way of sort of organizing where electrons are located and what behavior they're having. And so we use something called orbital notations and electron configuration. And this lesson is about how to write orbital notations and electron configurations. They are sort of an inventory to help us figure out where the electrons are located and what they're doing. All right, let's go back to your periodic table here. And let's also get out the notes that we took on the S, P, D, and F sublevel, the electron energy sublevel notes we took yesterday. So that's that table right there, okay, or the outline we had yesterday. Because what we're going to start doing now kind of requires both these tools. Now eventually, I'm hoping, in fact for the test, you're not going to have this. You're going to have to know this by memory. By the time we get to the test, I hope you're going to know what the S sublevel region, P sublevel region, D sublevel region, and F sublevel region are. Okay, and where they are on the periodic table without needing this reference. Okay. What we're going to do is we're going to start writing what is called orbital notation. Orbital notation. Anybody here ever been and worked in a store or business where they took inventory? Okay, what's inventory mean?
You take account of how much you start using it.
Okay, but you also have a list of where it's found, yes? No?
I mean, we just had the cooler section with like freezer names.
But I mean, it was in the cooler or the freezer. It was an inventory in the cooler or the inventory in the freezer, yes? So you kind of, so while you might not have realized what you're doing, you were basically saying how much was there and where it was located, okay? Well, an orbital notation is kind of like that. What we're doing is taking a kind of inventory of all the electrons in the electron cloud, where they're located, okay? And so we're going to start with the smallest and simplest atom, hydrogen. And looking at your periodic table outline we had yesterday, what region of the periodic table in terms of S, P, D, and F sublevels, electron energy sublevel regions, what region is the hydrogen atom located? S. Okay. So looking here, we're looking at, when we're doing orbital notation, we're only looking at what are called ground state atoms, those in the lowest energy state. So none of the electrons have been so excited they moved to a different orbital or a different energy level, but they're all in their ground lowest energy state. And so hydrogen is going to have, since it has one proton, that's what the atomic number here tells you, there's one proton in a hydrogen atom, not in a hydrogen ion, but a hydrogen atom is one proton, and so there's only one electron in a hydrogen, okay? So we're going to write the symbol for hydrogen. When you're writing orbital notation, you must include the atomic symbol, and then you put a colon after it, okay? And then you sort of drop down a bit and write that number 1, not because it's the number 1 atom, but because it's in the first row, which we call a period. Since it's in the first period, then this is a number 1 here, okay? And the sublevel is designated as a small letter S next to that 1, okay? What we're going to look at is where those electrons are located in an inventory. It doesn't mean what the location looks like, okay? The inventory that you were talking about a moment ago, where you're counting everything in the freezer, you just put on the piece of paper it's in the freezer. You don't have a picture of the freezer, okay? So we're not drawing what an actual orbital looks like. We just have a representation to indicate that it's in an orbital. Instead of writing out the word orbital, we're just going to use a box to show where that is. It's an orbital in the 1s sublevel. The sublevel is in the first primary energy level, The sublevel is called S, and the orbital is here. There's only one orbital in an S sublevel. Okay? Only one orbital in any S sublevel. And there's a whole bunch of S sublevels on this periodic table, are represented by the position of the atoms or elements on this periodic table. And since hydrogen only has one electron, we need a way of representing it. Well, the way we use to represent it has to do with what's called the spin of the electron. And so we use what's called, it's an up pointing arrow. I like to have a half arrow just because it's faster. But you can finish the arrow if you want to. Okay? Now, the reason that we say that electrons have spins is this. When you were in physical science, you may have done a demonstration or a lab where you took two things that had the same charge and put them next to each other. Did you do that with maybe pith balls or something? You don't remember that? Anyway, what happens when you put two things with the same charge next to each other? Huh? They fly apart. Okay? Well, electrons have the same charge. They're all negative. So conceivably, when you put them in the same area, they ought to fly apart. But then we have something strange that happens at this subatomic level. Remember, things don't always behave at the subatomic level in the way they behave at our level, where we can see them and taste them and touch them and so forth. Okay? They behave in strange ways. And the strange thing that happens between electrons is called quantum entanglement. Now, you don't have to know that term. All right? But I like the term because it kind of explains what's going on. The electrons, you could say, it's not really what's happening, but you could say electrons are talking to each other. Okay? Two electrons that ought to fly apart will stay close to each other regardless. Okay? Because they're quantumly entangled. But only two. 3 electrons won't do it. 4 electrons won't do it. Only 2 electrons can be quantumly entangled. Okay? And we designate that as a spin. The reason we use spin has to do with behavior of electricity, which is made up of a lot of electrons. When electrons are flowing in one direction, they create a magnetic field in what's called the right-hand rule. The right-hand rule says if I have my right hand and my thumb points the direction that the flow of electrons are going, then the field goes in this direction. So if I have electrons flowing in this direction on a wire, I have a field that goes in this direction. If I flow back in the opposite direction, the field goes in this direction, and they cancel each other out. So what we're saying here is, by the same token, there's a property that seems to follow this same concept. Okay, it may actually be a spin. All right, but somehow or other, we're allowing the electrons to cancel what is otherwise a repulsion, an electromagnetic repulsion. Okay, so we're going to have opposite spins when we get to the next atom. Okay, that's when we show a spin. But that's the orbital notation for hydrogen. We stop right there. Okay, we get to helium, we got to see where that spin comes in. You got it? You with me so far? All right. Now, as we build it up, some of this makes more and more sense as we go along because we use it more. Okay, so let's do helium now. Got to have the atomic symbol and a colon. Got to write the period helium is found in. Actually, where these electrons we're going to deal with are found. Okay, because later on we're going to have more than one period involved. All right, so that's period. What period is helium in? Well, that's in column 18, which is our family or group. Period 1. Periods are this way, going side to side. Okay? So it's in 1. And what sublevel do you find when you get to that helium? What sublevel region is it located in that periodic table outline? What? S. Still an S because we moved the helium from over here to over here. Okay? That's the reason we did that. So this is 1s. And S sublevels only have one orbital, which is designated as a square, although it's not the actual shape of an orbital. The actual shape of an orbital is different for different kinds of orbitals. Okay? And how many electrons do we have in the electron cloud of helium? 2 of them. And so one of the spins are going to go up, and so that they can cancel out and fit in the same region and not repulse each other, the second spin has to go down. Does that make sense? All right. Now let's go to lithium. That's our next element. So located on the periodic table, make sure you know what we're talking about. The more you visualize and look at where we're doing things on the periodic table, the more it's going to help you when we actually get to the more complex things here shortly. Okay? So lithium has electrons in 1s. Even though lithium is located on the second row, which makes it in the second period, okay? Second row, second period, the electrons in 1s are still there. Okay? The electrons in 1s are going to be there. But we're going to need some electrons in 2s now. Okay? This is the second row, second period, S sublevel region. Okay? So not only are we going to have the 1s electrons, we're going to have the 2s electrons. We can't put everything in 2s because 2s only has one orbital, and one orbital will only handle 2 electrons, and we need how many? We need 3 electrons. Okay? Got a Roman an atomic number of 3. That means 3 protons, and for an atom, it also means it has 3 electrons. Okay? All right. So what we do is just start from the beginning. All right. The first electron goes right here. The second electron goes right here, and that third electron is put into 2s. Well, you're not supposed to understand it yet. It will make sense as we do more of it. What? Because lithiums have 1s electrons and 2s electrons. Okay? All right. Think you can do beryllium for yourself? Try it out. See if you can figure out beryllium's orbital notation now based on what I've told you. Okay, how'd you do? You got it right? Everybody else get it right? See, that wasn't so hard, was it? Okay. Well, now let's step it up a notch. Okay? Because now we're going to go from over here in the S sublevel region to over here, which is the P sublevel region. Okay? P sublevel regions are different than S sublevel regions. S sublevel regions only have one orbital in that S sublevel. The P sublevel, there are 1, 2, 3, 4, 5, 6 atoms here on the periodic table, elements on the periodic table, representing the fact that we're going to put 1, 2, 3, 4, 5, 6 electrons in this P sublevel. And how many electrons can you put in an orbital? How many? Only 2. So if I can only put 2 electrons in an orbital, I've got 6 electrons to put in here, represented by these 6 elements here. How many orbitals do I need? 3. Okay? All right, that's how it works. So let's go to boron. All right, we got 1s, and you got some electrons there. Got 2 electrons in 1s. You got 2s because boron's in the second row of the periodic table. It's in the second row here, which means it's in the second period. So we can fill both the first period, or the first level of energy, and the second level of energy. And there's 2 electrons in 2s, and then we get to 2p, but we need 3 boxes here because there are 3 orbitals in the p sublevel. Okay? But we only need 1 electron. Okay? Only 1 more electron, because boron only has 5 electrons. Its atomic number is 5, which means the atom has 5 electrons, and that's a total of 5 electrons. Now, the 2 orbitals here, they're there even though there's nothing in them. Okay? For most of you, for a lot of you, right now, your parents are gone to work and siblings are gone to school, so your house is empty, right? Does that mean there's no house? No, the house is there. It's just empty. Well, the orbitals are there, even though the electrons are not there. Okay? All right, let's go to carbon.
So why do we have the empty orbitals? Like, why are they even there?
Because they're there. Just because they're there. I mean, you know, the house doesn't disappear because you go to school, right?
What are they for then?
What are they for? There is space available for electrons, even though they're not being used. Well, later on, when we start talking about bonding, we'll use that space. Okay, you just need to know they're there. Okay? All right, so for carbon, we're going to have our 1s electrons and our 2s electrons. And we're in 2p, and we have 3 orbitals. Now, here's where you got to know something kind of new about the way that electrons fill orbitals. Okay? And I like to think of it as the school bus rule. That's not what it's really called, but I like to call it the school bus rule. Okay, so I'm going to tell you a little story. All right? Everybody listening to my story? Okay? So this is Will's first day of school. Okay, and he's riding the bus. All right? He's the first person on the bus route. Okay, Will, what seat do you sit on if you're the first person on the bus bus route? First seat. Okay, he just gets in there and sits at the first seat. All right, good. All right, Mark's the second person on the bus route. First day at school, first year. Okay, Mark, you don't know Will. Where do you sit? You sit by him even though you don't know him? Do you really? He goes straight to the back of the bus, he said. That's not good. You just go to another seat, right? All right. All right. Y'all don't probably know the history about the back of the bus stuff. That's,
we do.
You do? Good. All right. Yeah. All right. If you don't know the history, ask me outside of class. It has nothing to do with chemistry. Okay. All right. But you sit in a different seat because you don't know. Well, you're not on the bus yet. Mark sits in a different seat because he doesn't know Will, right? He didn't know whether Will's going to bite him or something, yeah. All right. Okay. All right. Well, Cortland's going to be the third person on the bus since he spoke up and said he's going to sit somewhere else. Okay. You're the third person, first year, first time you're on the bus. Where are you going to sit? Another seat. Yes. Okay. All right. So there's only 3 seats on this bus. That's a really small bus because we only got 3 orbitals here. Okay. Only 3 seats on the bus. All right. Got 3 students in 3 separate seats. Only 3 seats on the bus. And Taylor's the next person on the route. First year at school. Doesn't know anybody. Doesn't know these 3 guys. Taylor, where are you going to sit?
Sit beside Will.
Beside Will. Okay. Beside another student. Okay. All right. Well, that's kind of what happens with filling up orbitals. Okay. You put one electron here, and the next electron goes here. And you don't pair them up until you have to pair them up. Does that make sense? Okay. You think you can do nitrogen for yourself now? Yeah, try nitrogen for yourself. You can work with a neighbor if you want to, but you can do nitrogen. Try it out. All right. Let's do nitrogen. How we doing? Okay. Now we get to that school bus rule thing where we've got people on 3 separate seats, and we're going to go back and put somebody here. Okay. So that's for oxygen. So 1s has 2 electrons, and 2s has 2 electrons, and 2p has 3 orbitals. We're going to need 4 electrons. 1, 2, 3, and then we can pair one up. So even though electrons can become quantumly entangled and fit in the same basic region of space, if they don't have to, they kind of don't. Okay? They're like those kindergartners in the first year on the bus. Okay? So I guess you guys now can do fluorine and neon. Okay, so please write the orbital notation for fluorine and neon to practice. All right? Let's see, the next one we come to is fluorine. Okay, and then neon. How'd you do? Everybody doing okay? All right, so Mallory, you getting a better grasp of what's going on now? You understanding now? Okay, just asking. Because you said that you didn't understand any of this.
I understand it better than I did before, but I'm not like 100%.
Okay. Well, let's go to sodium now. Okay. So now we're going to a new primary energy level. Okay. So sodium has all the electrons that neon had. But it's got one more electron than neon has. And we're in a new row of the periodic table called a period. So this is going to be 1, 2, 3, the third period. Okay? And what sublevel are we in over there? S. And there's only one orbital in a S sublevel, and we only need one more electron. So how'd you do? It's not so bad, is it? Okay? Why don't you do magnesium? Now, while I'm talking about that, students often confuse magnesium and manganese. They are two different elements. Don't get them confused. Magnesium is capital M, little g. Manganese is capital M, little n. Okay? How'd you do? Everybody's doing okay? All right, so our next element is aluminum. Think you can do aluminum for yourself? Okay, follows the same pattern as in the previous row, so just do aluminum for us, okay? Try it out. How'd you do? Everybody got the same thing I got right here? Okay. So this pattern just keeps repeating itself, okay? Why don't we skip over now and just do chlorine, all right? Rather than do every single atom, because we're kind of following the same pattern, and based on what I'm seeing from you guys and hearing from you guys, you're all doing pretty well on this. Let's do chlorine next. Okay, how'd you all do? Why do we have the 3s? Because there are electrons in 3s. How are you going to get to 17 electrons if you don't have electrons in 3s? Chlorine has an atomic number of 17, okay, which means that an atom of chlorine also has 17 electrons. 2, 4, 6, 8, 10, 12, 14, 16, and that's 17 right there. So if you don't have 3s, you'd only have 15 electrons. Okay, once you fill a sublevel as you work your way up, you keep that sublevel there. Okay, for every subsequent atom. Yes. Okay. All right. I've already done argon for you. I want you to notice something about all the elements in the last column of the periodic table here. Okay. Go ahead. What have you noticed?
3 boxes.
Okay, so and in fact what's really critical is all the orbitals in the third primary level, whatever the highest energy level is for that atom, they're completely full. So 3s and 3p are completely full for argon, a noble gas. Neons, 2s and 2p are completely full. That's a noble gas. Well, helium only has an S sublevel. It doesn't have any P sublevels. So its highest energy level is completely full as well, even though it only has an S sublevel there. That makes sense? And that's how the electrons arrange themselves in the orbital notation and electron configuration. We'll talk about that next. For noble gases, they have a completely full outer energy level, and that's called the valence level, okay? A valence level is the highest primary electron energy level for an atom. Okay? Oh, sorry. Valence level is the highest primary electron energy level for an atom. And noble gases are completely full at the valence level. Okay? Everybody got it? All right. So now we're going to go to the next row. Let's all do calcium together here. We're going to skip over potassium and go straight to calcium. So all the sublevels that were filled previously are also going to be filled here. And so we're going to add an extra electron in a new primary energy level corresponding to the period on the periodic table. Okay, each time we go to this large coefficient number here to a higher number, that's a primary energy level we're going to. These coefficient numbers here, here, those coefficient numbers represent a primary energy level. The S and P we've been talking about, those represent an energy sublevel. Okay? Primary energy level, sublevel. Primary energy level, sublevel. Primary energy level, sublevel, and so forth. So with calcium now, we're going to need 2 more electrons. We're in the 4th energy level here. 1, 2, 3, 4, the 4th period, meaning we're putting electrons in the 4th primary energy level of the actual atom. And we need 2 more electrons. Okay? Now the maximum number of electrons you can have in the highest primary energy level of an atom is 8. Okay, the maximum number of electrons you can have in the highest primary energy level of an atom is 8. In a ground state atom's highest electron energy level, okay, and that's called an octet. And you probably heard the word or the phrase octet rule before. Okay, we get into some exceptions when we start to do bonding, but for a ground state atom, you can only have a maximum, the ceiling, the top number of electrons you can have in the highest energy level is 8. Well, that poses a problem when we get into these atoms, especially over here. Because if I'm going to have 8 electrons, this row right here represents the filling of 10 extra electrons. Okay, well, the reason that they're placed where they are, the reason that we have these two primary levels here has to do with where these electrons are going to go. They're not going to go to the highest energy level. Okay, now, in reality, when you put in the first couple of electrons, they're even higher energy, but we treat them in high school as if they're not, just to keep everything simple and figure out how to write open rotation electron configurations correctly. Okay, so we're going to go and do scandium next. I'm going to do it with you. Okay, so we need all the same electrons we had with calcium. Okay, we need one more electron, and it can't be in the same energy level that will put it in the highest energy. It can't be in the highest energy level, because when we get over here to gallium, germanium, arsenic, and so forth, those are going to have electrons in the highest energy level. So these electrons actually have to be placed in a lower energy level. Okay, so these electrons, and that's what sublevel region is this on that outline we did? What sublevel region is that? D, okay? So this is the D sublevel region, but it's not going to be in the highest energy level. It's going to be in one energy level lower. This is 3D. And since I have 10 elements across this region right here, okay, that represents putting 10 electrons in that sublevel, and that means we need how many orbitals? Two in each? 5. 2 in each orbital, 10 electrons, we need 5 orbitals. 1, 2, 3, 4, 5. So we're going to put 1 electron right there. All right, now, I want to talk a little theory next, just to kind of make sure we're kind of clear on what we're doing. So, remember from your physical science class, you've got a nucleus, okay, and you've got these energy sublevels around it, around which we put electrons. Remember doing that in physical science? Okay. And then when we get to this level right here, we said we could put 18 electrons. But here's the problem. You can't put 18 electrons in here initially. Okay, you can only put 8 to start with. Okay, which corresponds to what we did when we filled up this level here, this second primary energy level, 8 electrons. Once we put some more electrons out here, 2 more electrons out here, then we can put electrons down in this region some more. Then there's more space in here. Okay? In fact, this is a 2-dimensional arrangement. What we're really talking about is 3 dimensions. So there's a great deal more space than these drawings even allow for. So once I put 2 electrons out here, I can put in this space that's available 10 more electrons, which is what we're doing here. We're putting 10 electrons in here. Does that make sense to everybody? Okay? So why don't you guys do iron next? Do iron next based on this same pattern. Iron. Okay, how'd you do? Okay. Makes sense? Now, we didn't get into the exceptions that occur. There are some exceptions in this filling order for like chromium, but we're not going to do that in this class. I just want to tell you right now there are exceptions. There are some strange sort of changes that happen in the way electrons fill up these energy levels, these orbitals, for some of the elements in the transition region. Okay, but we're just not going. We're going to pretend they don't exist for chemistry at this level in this class. Okay, you with me? So when you go to college and they ask you to know the exceptions, well, that's just something you got to do. Okay? And if you need help, come back and see me. I'll help you. All right? When you're in college, you can come back and see me. I'll help you. All right? Questions so far? Everybody all set with this? So, based on what you know now, you should be able to write orbital notations all the way up through lanthanum. Look on your periodic table and find lanthanum. Look on your periodic table and find lanthanum. Following this same pattern, you should be able to write orbital notation all the way up through lanthanum. Okay? So let me assign some homework for you. And then we'll move on to electron configurations. Let's do it for copper and ruthenium. Okay? Copper and ruthenium. So electron configurations are really simple once you understand orbital notations. That's what we're going to do next. And it's just kind of a condensed version of the orbital notation. Okay? So for electron configuration, we're going to write the element symbol and a colon, just like we did with orbital notation. Okay? But we're not going to use the boxes. We're just going to count the electrons in a sublevel. Let me show you how that works. We're going to write 1s on the same line as the symbol for lithium. Instead of dropping it down as we did up here, we're going to write it on the same line. We're going to count all the electrons in 1s and use that, or write that as a superscript. And then we're going to do the same thing for 2s, only in 2s there's only one electron. And that's the electron configuration for lithium. Does that make sense?
It's a lot easier than whatever I was just doing.
What?
I said it's a lot easier than whatever I was just doing.
Well, sure, but what it doesn't show you are the orbitals and the spin of electrons. Okay? All right, let's skip down to, say, nitrogen down here. Here's nitrogen. And let's write the electron configuration for that. Got an element symbol, got a primary energy level, and a sublevel, and we count the electrons there, 2. And we've got a primary energy level, 2, and a sublevel S, and 2 electrons there. And then we go to this primary energy level 2p and count the electrons. We've got 3 of those. And so that's the electron configuration for nitrogen. Everybody got that? All right, so let's let you practice now. Why don't you guys do an electron configuration, write an electron configuration for sodium. Write the electron configuration for sodium. All right, so here's the electron configuration I have for sodium. How'd you guys do? How'd I get what? Okay. There are how many electrons in this? That makes sense? Okay, so the question was, how did I get 2p6? I just count the electrons in that sublevel. All the electrons in those orbitals. Okay? Huh?
You have to do the orbital notation first to be able to...
No, you don't. You could go straight to electron configuration if that's what the question calls for. Okay? I think it's easier to write the orbital notation first when you're first starting out. Okay? And now you guys know how to write orbital notations and electron configurations for your elements on your element cube, which is due when? Thursday. Now, we're not going to get into the F sublevel region, so what you have to do is just look it up. And I'm going to tell you something about the orbital notation that you use on your element cube. Do I have everybody's attention? Orbital notations have no shorthand version. We're going to talk about the shorthand version of these in a second. But for your element cube, you can use a shorthand because there's not going to be enough room for some of you to do the orbital notation for some of your elements in the space you have. Okay? We'll talk about that in a minute. Now, there is a shorthand version for electron configurations, but we don't use it for small stuff like this. We only use it when we get to the big stuff. Okay? So let's do a big one. Okay? Let's let you do one we've kind of skipped over, like the orbital notation and the electron configuration for vanadium, and I'll show you how to do the shorthand version. Okay? Vanadium. Find it on your periodic table and do the electron configuration and orbital notation for vanadium. All right, so here's the orbital notation for vanadium. Check yours against mine. Here's the electron configuration. Got it?
Actually, okay, no. The only thing that I did wrong is that, like, 3D, I put 2 in the first one and then 1 in the next one.
You can't put 2 in an orbital if there's still an empty orbital over here. You got to remember. You got to put like the school bus rule. Okay.
How many points would I have gotten off if I did everything right?
Probably 1 point out of, I don't know, whatever it is, 6 or something. I don't know. Okay. All right. But now you know, and now you can fix it for the next time. Right? And there's not a quiz and a test yet. All right. Don't put anything away yet. We're not done yet. I still got you for about 4 more minutes, and I got things to do. I'm going to show you what's called the kernel electron configuration, like the kernel of corn. We call it in the South and in America, kernels, like a rank in the military. We call it the same thing, but it's not really the same thing. Okay, that's C-O-L-O-N-E-L. It's colonel.
Oh
Okay.
my gosh, that makes me so mad. That is my biggest pet peeve of that word that you,
Okay, well, let's don't say that word anymore then, since it's her pet peeve. Okay, it's also sometimes called a shorthand electron configuration or an abbreviated electron configuration. Okay, well, here's what we're going to do. Now, you really can't do it for orbital notation, but I'm going to let you do it for your element cube, only because otherwise you wouldn't have the space for some of these. Okay, and what you do is you find what part of this electron configuration fits the next lowest or next smaller noble gas. So vanadium's next smaller noble gas, here's vanadium, count backwards, 1, 2, 3, 4. I just hit a noble gas right here. That's the next lowest noble gas. What we're going to do is to replace that part of this electron configuration that is also argon's electron configuration and replace it with the symbol for argon. Now let me show you how that works. Here's vanadium. Here's that colon. And this part right here, between my fingers, is the orbital notation, or electron configuration rather, for argon. So I can replace all of that with the symbol for argon in brackets. And all I have to do is write what's on the end. So that then is the kernel electron configuration, K-E-R-N-A-L, like the kernel of corn, which is also sometimes just called the shorthand version or abbreviated version. Yes? Sure. There you go. Yep. Now, so on the homework, we're going to add that you're going to also write the electron configurations, and kernel electron configurations.
orbital rotation, electron configuration,
Pretty much everything you learned today.
for copper and
Ruthenium, yes. Okay? Does that make sense? Yeah. Since we all learned today, now you got to go home and practice it on your own to try and solidify it in your head so you can ace the next test.